So welcome to the 908th monthly meeting of the Amateur Telescope Makers of Boston. We have a speaker today, Gregory Shanos. He's speaking with us through Zoom. So he's going to talk to us about a topic, Journey to a Comet. So as part of the President's Welcome, I want to share with you a couple of, I think, relevant stories that I enjoyed. Let me just get to the... So I make some travels and I happened to go to Death Valley, so I have never gone to a Bottle 1 sky, so I have not seen a sky like that before. So all I could do was to guess.
Dim the lights.
Oh, okay.
Let's see which one works best.
Yeah. So this was about half an hour of exposure, and what you see on the left-hand corner is Las Vegas lights reflected on the eastern side. So even though it is Bottle 1, you will see on the east the glow of the Las Vegas, and also on the southwest you see the Los Angeles lights. So light pollution is still everywhere. Just want to mention that, that's very important to note. But I took a similar picture with similar settings from my backyard some time ago, and you don't see that many stars even after double the time of exposure that I had. So I was quite happy to see this one.
Why did the mountains come out bluish like that?
I may be in the processing wise, I may have exposed it, it is just, it is, and I should do a little bit better understanding of star trailing. Yeah, but pretty much. It did look, because of some of the colors even during the daytime, because of the presence of the minerals, it's borax in the front and it's salt. So I think we have Corey, who was there also a day before, I think, when I went there.
Almost ran into each other.
Yeah, so that's one story I wanted to share about this light pollution, even in a Bottle 1 sky. Yesterday, Bruce and I and several others from ATMoB joined a astronomy on the tap at a session in Somerville, and I was quite impressed by the crowd that was there. And this is I took the picture of this crowd, and if you look at it, they're all youngsters, and the average age between 25 to 35. And I asked many of them as to what motivated them to come here, and the topic was about dark energy and dark matter. So they all pointed me to this particular Instagram post that Astronomy on Tap Boston presented. There were 3 postings that they had of these speakers, and they were all sitting there for an hour and a half and listening. So I'm just saying that, from the recent discussions of what we are having with social media and how we can approach it in a useful manner. So there are people using it. Even one of our presentations of ATMoB, a solar viewing party, the Carey Memorial Library had it, and we had about 70 people who came. Chris, Richard, you can correct me if I'm wrong.
That's about right.
Pretty much about half a dozen people I spoke to all pointed to this Instagram post that motivated them to come. So I have not seen this until I did a search yesterday that this was the posting that they had. So that was some of the reasonings that I used, that we should use social media in a more appropriate way. So yeah. So that was the 2 stories I wanted to share, and I think I also want to ask Mario to introduce our distinguished visitor here.
Now?
Yeah, why not we do that, and then we'll go to the next session.
Is Mario the distinguished visitor?
Yes, he too.
No, I'm not distinguished.
We don't. You're not extinguished either, so that's
Yeah, the abuse is unbelievable.
I'm sure everyone knows Steve O'Mara by now, and his lovely wife Debs is here. Does anyone not know who Steve O'Mara is? I'm not going to give the usual spiel. I mean, he, for people online who may not, he found, observing right on the roof over here with the 9-inch, he saw an unusual what he thought was an artifact. I'm not sure what you thought when you first saw this, but he found spokes on Saturn, right? And he told people about it, including me. He was a teenager at the time, and I was at Boston College, came here intermittently in meetings. And I, like many other people, looked at him and said, sure. So I immediately discounted it, and professorially, as his elder, tried to explain to him how impossible that is with differential rotation. And then, of course, we all know what happened when Voyager 1 went by Saturn and saw pictures of spokes. And everyone was scratching their head, including me, and said, wow. And it turns out it's levitating magnetic field lines of dark matter, which are levitating right above the rings. So I learned a couple of things from that. One is trust your eyes when you see something, report what you see. And two, if Steve sees it, believe him, no matter what it is, just believe him. Okay, he also determined the rotation period of Uranus before anyone else. So I think it's because I mocked him, that he's been trying to kill me ever since. And so I visited him in Hawaii. He lived in Hawaii for many, many years. And I'll just give this one vignette, and I think it summarizes it pretty well. So we went out at night because the volcano was erupting. And it was just beautiful watching the lava glowing red flowing down. And he tells me, why don't you stand on that mountain and I'll take a great picture of you with the lava behind you. I go, okay. So I stand there and it felt kind of warm. I go, Steve, this is hot. And he goes, don't worry about it. And so he's taking pictures. And I go, can I get off now? My gonads are getting a little hot. So we get off, he's done with the pictures, and we turn around and look where I was standing to take one more picture, and just at that moment where I was standing, the ground opened up and the lava came flowing out. So, and there's a few other episodes that I can tell you about, but I won't. But anyway, Steve, I've also had the pleasure of giving him images for his books. But that's enough about our reminiscences. Let Steve come up and talk, much more interesting. Come up here, say something.
Say something.
Say something.
Thank you, Mario. I didn't get you in Hawaii, so now you have to come to Botswana. There's a leopard I want you to see. I guess what I want to say is, because I'm on the spot here, is thank you to the ATMs of Boston. Okay, so I first came here under Mario and Sal, and it was like 1970. And I was just a kid. I have to tell you, my first time I gave a talk, it was in this auditorium. And everyone was here and some guys were smoking a pipe. And I was gonna give a talk about galaxies and Leo, Mario, and all that. And I got up here and I just stood and stared. And not a word came out of my mouth. And I stood and stared. Stage fright, I mean, I was like, what, 13, 14? And I think it was Mario and Denise Chico started asking me questions. And that loosened me up and I was able to speak. And I guess, so now, like 55, almost 60 years later, whatever, here I am, speaking to you. So, I want to thank you because it's very important, everyone, Dick, and you're also very special to me. And what I find kind of amazing, and I just thought of this on the way coming here, is that next year is 2026, and that's 50 years since I first saw the spokes in Saturn's rings. Wow. I know. That's 50 years. And so it seems like yesterday. And it's with that little 9-inch up there. And that it was the same scope that I found the rotation period of Uranus. And that wasn't even my doing. Brad Smith, the Voyager imaging team leader, after I found the spokes, said, okay, he called me up. He said, okay, Mr. Smarty Pants. He said, okay, Mr. Smarty Pants. How about you look at Uranus before Voyager gets there and see if you can determine the rotation period. And so I was like, oh, well, okay. And he said he was going to be using a 24-inch down in Texas, or Chile, and someone else was using a 24-inch or an 80-something inch down somewhere. I forget the details. And they were going to use CCDs and all this stuff. And in the end, they got 24-hour rotation period, and I got 16.3. And then Voyager got out there, and they got 16.2. So, yeah, and I was able to publish that. I was able to publish that on a circular right before it came out. But that was done with the 9-inch. And it took years, you know, it was years, how many years before Voyager got there. And I just sat there and watched Uranus until I saw a little cloud on the planet. And it was so bright, that cloud was so bright, I ran downstairs and I got Mike Rodenko, I got Peter Collins, I said, look at Uranus and tell me what you see. And they all said, I see a planetary nebula with a double star in the center. And the double star were 2 clouds on Uranus. And I used those clouds to determine the rotation period. And I guess the other thing that was great about this telescope was that it was the telescope I used to practice for the field of Halley's Comet. You know, I recovered Halley's Comet in 1985 when it was magnitude 19.6. That was because I used the telescope of Mauna Kea, 24-inch planetary control telescope, 14,000 feet, breathing bottled oxygen, all that stuff. And it was because of a grand foible that led to the finding of Halley's Comet, because I searched for the field in practice here at the 9-inch, then I went out to Hawaii, and because of the altitude, 40% of the oxygen gone, I started looking to where the comet should be in Cambridge instead of Hawaii. So it's a 6-hour difference, and the comet moves in 6 hours. So I plotted stars on my chart, and the first thing that I did was, because they were imaging it with the 88-inch, I went over and I said, I don't see Halley's Comet, but I said, so it must be really faint because I'm seeing a lot of stars that even on the Palomar. And they looked at my finding chart and said, well, your finding chart doesn't show the stars, all the stars that are on the Palomar Sky Survey, but you are plotting stars as faint as the Palomar Sky Survey. And they said, we think you can do it, so go back out. So it was because of that error that, you know, gave me the confidence that I could do this. And anyway, I was able to see the comet. But anyway, again, thanks everyone for many, many years of happiness here in Cambridge and part of the ATMoBs of Boston. You'll be a part of my life forever. Lots of old friends here. And we should get on to the real speaker next. Thank you.
So I think Rich and
It's time for the observer's report. We have a Comet speaker tonight, so I thought I would put this headline up from 1910, almost exactly 115 years ago, before we knew all that much about comets. I always like to tell the story about comets in the sense that we've come a long way. If you think back to Halley's Comet in particular, when it was rounding the sun in 1835, astronomers could merely sketch the comet using their telescopes. By 1910, they could not only take photographs of the comet, but they could look at the chemical composition because the science of spectroscopy had come along. By the next pass, in 1985-86, we were sending a fleet of spacecraft to image the comet. And we've come a long way. We know a lot about comets. Of course, these spheres back then were unfounded, despite the fact that they had seen some scary chemicals in the tail of a comet. You've probably heard that comets' tails are about as close to nothing as anything can be and still be something. They're pretty diffuse. So I thought I would just put that up there as just a prelude to tonight's speaker. Next slide, please, is the quote, David Levy's famous quote, "Comets are like cats, they have tails and they do precisely what they want." We have all experienced that with comets. The comet that was just most recently in the news, Comet Swan, fizzled away to nothing. Some comets are wonderful, some comets have the potential to be wonderful. You get what you get, they're like cats. Anyway, let's get going here. We're running out of planets in the evening sky. I don't know if you've been noticing. It's been pretty cloudy and pretty rainy, but if you've had a clear break in the skies, you notice that we're running out of planets. Jupiter is actually setting around 10:30 p.m. only because of its high northern declination. It's up still pretty late, but at sunset, it's less than 30 degrees at altitude with superior conjunction occurring on the 24th of June. So our season for observing Jupiter is nearly over. Mars, of course, remains disappointing. It's always disappointing. 1.5, well, not really, but most of the time disappointing. 1.5 astronomical units away, it's only 6.3 arc seconds, magnitude 1. Uranus is setting in a bright sky just after sunset. Next slide, please. Probably says sunset on the next slide. There we go. Venus, Saturn, and Neptune are visible in the morning sky. They're still clustered in the east-southeast just before sunrise. Venus, of course, is easy to see. Saturn is getting easier. Neptune is still a little bit of a challenge because the ecliptic in the morning skies in May still presents a pretty shallow angle with respect to the horizon. So it's a little bit tricky, but of course, as I always try to inspire you to do, try naked eye and telescopic observations of Venus. It's 43 degrees away from the sun. Greatest elongation occurs on May 31st. The moon will join these planets on the 22nd, 23rd of, that's supposed to say May. And Mercury is very low in the east during dawn, superior conjunctions on May 29th. So there aren't too many planets to look at once you get up, catch Jupiter in the evening and some of these guys in the morning skies. I'm gonna put I'm doing this, I'm gonna dedicate these slides forevermore to Mario, of course, our preeminent lunar observer. I'm gonna include a lunar highlight of the month. The moon presents a little over 50% of its visible surface to us due to the librations that occur. And as it turns out, later this month in May, there'll be a great opportunity to see the Rook and Cordillera Mountains, which encircle the Oriental Basin. And so this shot over here is just from it's called Moon HD. It's an app I like to use. And it really is quite good at representing exactly what you're going to see through a telescope. So there are those little fingery kind of lava lakes over there are where you want to look. And here they are presented here with the Oriental Basin. So I'm going to try and inspire you all to get out and get back to moon observing every now and again. So that's something to look for. You don't get to see those guys very often, and so the librations are kind of perfect for it later this month. Next slide, please. So, is Glenn, are you here? I just want to see. Online. Is he online? Is Glenn here?
Yeah, can you hear me?
Yeah, okay, I just wanted to see if you were here. Because Glenn loves double stars, and so he was really happy when I picked this double star for the month. It's Portland. It's Gamma Virginis, and it's STF 1670. It's a really, really pretty double star, maybe a little bit of a challenge in small scopes, because the pair of almost identical stars are only 3.5 arc seconds away from each other. And that, Glenn, correct me if I'm correct, help me out here, that's improving, yes?
Yes, it is. It might even be about 4 arc second separation now.
Well, according to Sky Safari Pro, they're still at 3.5. And those guys are pretty good. But anyway, it can be a little bit challenging. A little aperture will help out. They're only 38 light years away. The period's 168 years. And the average separation of the stars, the physical separation, is only 40 astronomical units. They're physically bound together in space, which I think makes it kind of interesting to look at them. So that's nice in the springtime skies. Get out there and look at Gamma Virginis. Next slide, please. The next slide is the variable star of the month, not TCRB, which we're still waiting on. But I picked on SS Virginis. It's a carbon star. Carbon stars are evolved stars. They pulsate with a fairly regular period. This one is 364 days. And it turns out that in this era, our lifetime here, the minima are occurring right about now. And the reason I'm happy to report that is because carbon stars tend to be at their reddest when they're at their faintest. So every year, just about this time, every single year, just about this time, the star is at its faintest, and therefore it is at its reddest. And if you like carbon stars, this is a beauty. Yes, sir.
Spectral class C6C, I've never heard of spectral class C. What is that?
You're gonna put me on the spot, John. OBA fine. Yeah, it's down there. It's really far down. I'll report that back to you next month.
Thank you.
That's homework for me to do.
I think from what I understood is it's now the carbon stars are given that spectral class C.
Oh, is it?
He said that he feels that now, these days, carbon stars are denoted with spectral class C.
Okay, see.
The carbon stars are red because they've been cooking up carbon in their cores. And convection has brought a lot of the carbon up to the surface of the stars, where it's cool enough for exotic carbon compounds to form. Compounds that you would have never been able to draw a Lewis structure for in your chemistry class back in high school. They defy all of that, but they're there. And so not only are these stars red because they are cool, but the carbon compounds and sootiness in the atmosphere of the stars scatters and absorbs blue light, making them even redder. So they're really cool stars to see. Joe Henry's a carbon star, loves those things. This is one of his favorites, so is V Hydra. And yes, sir.
I don't know if this is a red herring, but just this morning I got a couple of reports that people observing T Corona say it's been fluctuating up and down rather rapidly. So something may be happening.
Okay.
It's going to be clear Saturday and Sunday night, maybe worth a look.
Corona Borealis is very well placed in the evening skies now for us. And so all you have to do is just go out and take a look. It currently is around 10th magnitude, but when it brightens, it'll be maybe as bright as 2nd magnitude, based on the last couple of outbursts. All you have to do is go out and look and go, well, there's a star there, and that's it. When you look at the light curves, it goes very fast, from 10th up to 3rd, 2nd magnitude. And I wonder if you could actually catch it in outbursts. Would you be able to see it changing brightness in real time? Would it be like somebody's turning up a dimmer switch on a light? Because the rise is very, very rapid. And it only stays near the peak.
It'll be cloudy. It'll be cloudy.
Right? Welcome to New England. Anyway, that color index of 4.19 really gives away its redness. This is a nice red star. You should check that out. All right, next slide, please. Okay, so Glenn's been having some problems with his computers, and we don't have a lot of pictures for these objects, but the main challenge continues to be NGC 4284, 4290. It's the galaxy pair in Ursa Major. It is really just adjacent to M40. And I don't know if you've ever seen M40. It is spectacular. Spectacular. It's a double stop. It's Winnock 4, which makes it pretty easy to find. It's on most star charts, but Messier must have thought it was not a comet, and so Winnock 4 is Messier 40. I tell people in the fall that M72, 3 is twice as exciting as M40. Twice as exciting, because it's 4 stars. Anyway, I still think you should get out there and try and look at these galaxies. They are pretty faint. Look at the surface brightness on these guys. 42.9 is a little bit easier to see with a surface brightness of 13.2. I've never seen this guy, 4284. That's really, really faint. You know, we're not on Mauna Kea, or we're not on the middle of Botswana, where you've got like magnitude 7 skies, right? We're
Texas.
in Texas is pretty. Some parts of Texas are pretty dark. But I have my own thoughts about these challenges. All right, how about what do we got for June? Well, there's Doug's. That we showed this last month. This is Doug's preliminary image. This is that PGC galaxy. This is not part of the challenge. I just pointed it out last time because I was amazed he actually picked it up. Doug, nice job on that. That's a faint galaxy right there. So nice job. Do you want to say anything more about this?
6-inch aperture, 4-hour exposure.
When you hear an imager tell you that it took 4 hours to get this image, don't let that dissuade you from going out and looking at these objects. They're probably a little bit more.
Actually, 6 hours of clock time, perhaps spread over 2 or more days.
Right.
You know,
Don't let that keep you inside watching TV. Get out there and observe. You can see those yourself.
but I watch TV while I'm imaging.
It's so 21st century, Doug.
Hey, it keeps me awake.
So this is an interesting galaxy group in Draco. I don't know if you've ever looked at this this group. NGC 5981, 82, and 85. They're pretty easy to see, and they're located. Here's the head of Draco. I don't know if you can see it on the slide. Here's Draco's body. There's NGC 6543, the Cat-Eye Nebula. Down here to Dosage, and then up here to Thuban, and then over by the Big Dipper. So they're right in this arc of Draco here, and it's a really nice galaxy trio. So I would really encourage you to get out and try and spot those. These are very high overhead in the early evening hours in May, and so it's a fairly easy target. If you're interested in looking, I didn't put it on here because I don't want to clutter it up, but if you jump off Adesich here and head this way just a little bit, you can come to a beautiful, Spain, but it's beautiful, NGC 5207. It's a nice edge-on galaxy.
5907?
Maybe, I can't remember the numbers very well.
Yeah.
This is 5907, and then just a skip and a hop up to what is thought to be M102. So,
An image of that is in June Sky and Tel.
oh, okay. Oh, perfect. All right, excellent. We'll all check out our June Sky and Tel.
So if anybody really needs to see them, I have all the images on my laptop here.
Perfect, thank you. Clubhouse is open May 16, 17, 23rd, 24th, and there are the dates in June. And then Glenn and I are going to attempt, again, to run an intro to the spring night sky. We've been clouded out every time we've tried to do it so far. But we're going to give it one more shot Friday, that's next Friday night, and then the rain date of Saturday, May 3rd. That
Time
doesn't
machine.
seem right, but, oh yeah, see it's got a little dark 17 here? Imagine this 17 is in yellow and this 3 is in here. And I will send out an email about that. And next slide, please. I'm just going to jump into the hours. Glenn, thank you for helping out with the report tonight.
Hey, my pleasure. Stay healthy and keep looking up.
Right, next to our speaker, Gregory Shanos. The title is Journey to a Comet. 6 spacecrafts have visited various comets from Giotto in 1986 to Rosetta in 2015. Our speaker is Dr. Gregory Shanos. Will discuss significant findings from all these missions, focusing on detection of organic molecules. Gregory Shanos is a pharmacist by profession and NASA Solar System ambassador by passion. He graduated from University of Rhode Island with a double baccalaureate in both pharmacy and chemistry, a Master of Arts in Teaching from Rhode Island College, and a Doctor of Pharmacy degree from University of Florida. Greg and his wife Denise currently lives in Sarasota, Florida. Greg is a member of the Skyscrapers, the Amateur Astronomical Society of Rhode Island, a local group of deep sky observers, Suncoast Stargazers in Sarasota, Bradenton, and the St. Peter's Astronomy Club. Dr. Shanos became an amateur astronomer in 1985 with the apparition of Halley's Comet. Dr. Shanos is an avid meteorite collector and has published over 35 review articles on the significance of organic molecules and meteorites. An avid eclipse chaser, Greg has witnessed 13 total solar eclipses, 4 annular and entire transits of Venus from Greece and Hawaii. Recent advances in digital technology have led Dr. Shanos in planetary and deep sky astrophotography. Greg's planetary images are archived with Association of Lunar and Planetary Observers. So all to you, Greg.
Before I start, I just want to mention, check the May issue of Sky and Telescope. They're going to be 11 shadow transits of Saturn. And the first one, actually the second one occurs May 15th, this coming Thursday, just before 6 a.m. It'll be right in the center of the planet. It'll be incredible. So make sure you check that out. Okay, so Journey to a Comet. Comets are the reason why I'm an amateur astronomer. I saw Halley's Comet back in 1986 with the skyscrapers, and I'll talk more about that. But just a historical, can you see my arrow
Yes.
moving? Okay, great. So comets have been known since antiquity. The first stone tablets here were in Mesopotamia in 2100 BCE. Chinese Atlas of Comets in 300. 164 BC, this is the first Babylonian mention of Halley's Comet. And then, interestingly enough, when Julius Caesar was assassinated in 44 BC, there was a comet a few days later, a bright naked eye comet that appeared, and Augustus declared this a sign of the deification of Julius Caesar. So, and then in the 4th century BC, Aristotle concluded that comets were emissions of Earth, were emissions from Earth that rose to the sky. And the reason for this was because the ancients, as you know, believed that the heavens were perfect and orderly. So a phenomenon as erratic and unexpected as a comet could not be from the perfect celestial sphere. Dead wrong. And then astrologers interpreted sudden appearances of comets as ill omens, presaging famine, flood, and death of kings. And then Halley's Comet was followed through the ages. And then in the Middle Ages, right here, there's Bayeux Tapestry, 1066. There's the comet right there. And people are like, oh, wow, and the king is ducking, so everyone's horrified by what this thing is. And if you look here, it kind of looks like a sword, too. It does look kind of menacing, it does. So that's why I think that the ancient sword is something bad. Kepler's discovery of the elliptical nature of orbits helped pave the way for better understanding of cometary motion. And then in 1705, Edmund Halley, along with Isaac Newton, found that the 3 comets during these dates had almost the same orbits and returned every 76 years. So Halley concluded they were the same comet and not 3 different comets. So he predicted the return in 1758, which indeed took place. Unfortunately, Halley died in 1742, so he never lived to see the comet come back. That's unfortunate. But the comet has been named after him since, he came up with the original idea that they were indeed the same comet. And then Halley showed that comets orbit the sun in elliptical paths. And then fast forward to 1950. Before that, the flying sandbank model was proposed, and that was the model, and that just meant that a cloud of meteoritic particles held together by their own gravity and interplanetary dust were absorbed on the surfaces, and they escaped when the comet came close to the sun, and the particles were heated raw. So that was before 1950 what astronomers thought comets were. And then in 1950, Fred Whipple, shown here, he actually spoke to skyscrapers on October 4th, 1986. And here he is at age 80, died 97. I hope I can live that long. And then here I am at age 27, and I'm 65 now, so hopefully I've aged gracefully. And so Whipple suggested that comets have an icy core inside an insulating layer of dirt, and the jets ejected from the solar heating that caused the orbital changes. So he was basically right. And so anatomy of the comet. So I'm going to go through each of these in the slides coming up. But the hydrogen envelope, an invisible layer of hydrogen surrounding the coma. Okay, so this is the basic anatomy of a comet. You have the nucleus, which forms the coma, and then interaction with the solar wind blows the dust away, and then ionizes the gas and forms a beautiful tail. So we'll talk more about this in detail. So this was Fred Whipple's original hypothesis, proposed in 1940. And so the nucleus is a solid central part of the comet composed of rock dust and frozen gases. And when heated, the gases sublime and produce an atmosphere surrounding the nucleus known as a coma. Sublimation, as you know, is a process of going from a solid to a gas. And you've all experienced this if you ever seen dry ice, and you see it go directly from a solid to a gas. And you'll never have liquid dry ice. It will just go directly to a gas. And most cometary nuclei, well, we'll talk about this, the density is very low. It's less than water, which would be 1 gram per cubic centimeter. The nucleus of comets tend to be very fragile because a lot of them split apart as they come closer to the sun. And they could split apart due to thermal stress, internal gas pressure, impact. And they're one of the darkest objects known to exist in the solar system. What's interesting is fresh asphalt reflects 7% of light that falls upon. Albedo is just a fancy term for reflectivity. A mirror would have theoretically 100% albedo, it will reflect all the light that it hits. But fresh asphalt reflects 7. Comets reflect 3 to 6%. So even less than asphalt. So they are jet black. They're very, very dark. So the coma. So the coma is the nebulous envelope formed around the nucleus of a comet, formed when the comet passes close to the sun. And that's what gives the comets that fuzzy appearance. And we talked about what sublimation is. And water dominates 90% of the volatiles. And usually the nuclei, and usually they form about 3 to 4 astronomical units from the sun. And water H2O is the parent molecule and is destroyed by photodissociation to H plus and OH minus. So if you look here, H2O, okay? So that's how water dissociates. And the coma usually contains other molecules such as ammonia, carbon dioxide, and cyanide. And this was a beautiful comet. I have my own photo of this at the very end. But this was like pure coma. This did not have a tail. It came out Comet Holmes in 2007. It just had this beautiful greenish round, and that was it. No tail at all. That's pretty unique. You don't get too many comets that don't show a tail. And then the dust tail. So dust tails start to form around the orbit of Mars. And the sun heats the nucleus, releasing gas and dust from the coma. The sunlight strikes the dust particles and exerts a pressure radiation, which pushes the dust particles from the coma and into a dust tail. And since they're different sizes and they all have a unique velocity, each has its own individual orbit, and it usually results in a broad dust tail. And it usually follows the motion of the comet, so they tend to appear curved. And most of it is smoke-sized grains, but there's larger grains that can be sheared off. And these larger grains form a meteor stream, which continues to orbit the sun in the same path as the comet. And when the Earth intersects this, we see a meteor shower. And okay, so the meteor shower is here. I live in Bortle 5 to 6 skies, just like southern New England, and it's just terrible. I mean, I'm lucky to see a 4th magnitude star up on the zenith. So the only ones that I actually observe are the Geminids and the Perseids. And being in Florida, the Geminids is very comfortable in the summertime. And I submitted my observations to ALPO and also to the International Meteor Organization. And I received the Meteor Award from the Astronomical League. 36 hours of observing meteors took me over 10 years to accomplish. I just got it a year or so ago. But what's interesting is the Perseids is from the comet Swift-Tuttle. And if you're ever in Sarasota, Mario, I know you reside, you have a place in Naples. If you're ever in Sarasota, go up Fruitville Road, and if you turn right, I turn left, it's Swift, and if you turn right, it's Tuttle. There's actually a road, major artery called Swift Tuttle in Sarasota. How cool is that? So that's pretty deep. So you all know about meteor showers. So plasma tail, the plasma tails form closer to the sun than dust tails, and they basically form because the ultraviolet sunlight rips one or more electrons from a gas, and that creates an ion positive. And then the ion tails are made of ionized gases, and if it's ionized, it's strongly influenced by the magnetic field of the solar wind. And then plasma tails appear more turbulent. You can see twists and knots here. And the ion tail follows the magnetic lines rather than the orbital trajectory, just like the dust tail follows more the orbital trajectory. That's why they're curved. But the plasma tails don't. They're usually very, very straight. And the bluish color is due to ionized carbon monoxide, CO plus. And Comet Hyakutake, I remember this comet. This was beautiful. And Hale Bob, they were within a year of each other. And this was before the digital age. So we all used film, fast film at this point. But this was a long period comet, which I'll talk about in a bit. And I won't be back for another 100,000 years. Rarer tails, the anti-tail. I have a little demonstration here on this. Where am I? Oh, here it is. Okay, so the anti-tail is a spike projecting from the comet's coma that seems to go towards the sun, and thus geometrically opposite the dust and ion tail. Phenomena is an optical illusion. The anti-tail is formed of larger dust particles, which are less affected by the sun's radiation and tend to remain roughly in the comet's orbital plane and form a disk. As the Earth passes through the comet's orbital plane, the disk seen side on and appears as a spike. The other side blends in and is lost. Anti-tails normally are visible only as the Earth passes through the comet's orbital plane. So can you see me here? Can you see this little demo I have here? So, huh?
Yeah.
Okay. So here's the nucleus, and this represents the plane of the dust tail. So this is the back of the tail, and this is the front. So what it's saying is that normally when you see the when you're looking at a comet, you're looking at it this way. But when you're looking at it side on and the comet Earth geometry is just right, it looks like this. And now you see the spike here, and this just blends into the background as the normal tail. See that? See, so this would just blend into the background. Here's the anti-tail. And then as you go like that, there's the nice thin line. See that? So it makes sense. So that's what all this is saying. And the one you see in the textbooks all the time is this comet Armand Roland, which occurred before I was born. And you see the nice spike there. And this is a photo I took of Chuchin-San Atlas, which was a great comet, on October 14, 2024. And if you look closely here, can you see anti-tail going down here? It was actually a huge anti-tail going way down, much larger than Armand Roland. And this is overlooking the Gulf of Mexico. And this is
You might want to resume your slides.
what?
You might want to resume your slideshow.
Oh, okay. Can you see it now?
Maybe on our upper screens. Our projector isn't great.
Yes.
Yeah, it should be. I see it full screen. Is it full screen now?
Yes.
Okay. All right. So if you look carefully here, you can see a anti-tail going down. See it? But if you can't, that's fine. But and I remember there was a full moon rising at the time. In the east. This is the west here, and this is talk about comets being forecasting doom. October 9th was Hurricane Milton, which Sarasota was the eye of a category 3 hurricane with sustained 120 mile an hour winds. And then 10 days before that, we had another hurricane hit, Helene, which caused a lot of flooding. So fortunately, I had minimal damage, but others weren't so fortunate. But but 5 days later, nice and calm and beautiful skies. So, okay. Another thing, a rare tail. This was only discovered when Hale-Bopp came out in 1997. There's a sodium tail, and this is really interesting. It lies right between the ion tail, which is here, or the plasma and ion tail are used interchangeably, and this is the dust tail. You have beautiful sodium tail here. Isn't that gorgeous? Now you need, it's neutral, so it's not ionized, but you need special filters and optical device. This was taken by McDonald Observatory. I actually visited that. It's in Texas. So, yeah, you need professional observatory to see this. But it's kind of neat. It's nice to know that it exists. And then interplanetary magnetic fields and sector boundary crossings. Okay, so as the solar wind flows away from the sun, it carries with it its magnetic field. And this has a spiral shape. And then usually you get 2 to 4 sectors. Here it shows 2, and they form kind of a sheet in 3 dimensions. And then these have separate polarities, these sheets. Okay, so why do I mention this? Because comets lose their tails, their plasma tails. How cool is that? Since they're ions are very prone to sensitive to magnetic fields. So 2 mechanisms are considered for disconnection events: ambient solar wind pressure, plasma instabilities in the tail, or the sector boundary crossing. In this case, Enki, this was a coronal mass ejection. So this sent a huge amount of plasma and magnetic disruption. And then notice as it's crossing here, the tail just gets cut right off, and a new tail grows in its place. So just like a lizard, it will grow a new tail. So that's kind of cool. Okay, orbits of comets. Comets are classified as either short period or long period comets. So the short period comets, such as Halley, have periods of a few years to decades. They have a lower orbital inclination to the solar system and prograde motion. They spin in the same direction as their orbit. Jupiter family comets are short period, but with periods less than 20 years. And they're named because they're much closer to the sun, and their gravitational attractions strongly influenced by Jupiter. And long period comets like Hyakutake took 18,400 years to get here. The inclination can be any inclination and could be retrograde as well as prograde, so it doesn't matter, but these have a much higher inclination than short period. So here's basically how it goes. The nucleus is all frozen. The coma forms when it's 5 times further from the sun. As it gets closer, the comet tail starts to form. The comet tails are always pointing away from the sun, because think of it, the radiation pressure from the sun is pushing the dust and the plasma out, and then it orbits like this, and then as it gets further away, the plasma and dust tails start to disappear because it gets colder, and then it's back out. So that's basically the orbits. And then where do comets come from? 2 places: the Kuiper Belt, which is a disc-shaped region beyond the orbit of Neptune and contains countless icy objects. And this is basically where the short period comets come from. And this was one of the reasons Pluto was demoted as a planet, because before we knew a lot of this, it's basically one of the closest Kuiper Belt object to us, basically. And that's one of the reasons it was demoted. And then the Oort cloud is where the long period comets come from. So the Kuiper Belt's 10 to the second AU. The Oort cloud is way out here at 10 to the fifth AU. And then comets are perturbed from the Oort cloud primarily by gravitational interactions with passing stars, giant molecular clouds, and gravitational tidal effects of the Milky Way. So these are the long period comets. Shoemaker-Levy comet. I'll bet most people have seen this. This happened in 1994. This was the first collision of a comet with another body of the solar system. And Jupiter actually trapped this comet into its gravitational field, shattered it into 20 discrete pieces, 1.2 miles on average, and impacted at 60 kilometers per second. And what was cool is it had these beautiful scars. Look at that. And I met Dave Levy on several occasions, but he autographed this during the solar eclipse expedition, March 27, 2006. He wrote, "To Greg, these exquisite drawings record the Shoemaker line impacts beautifully." And then I have over 40 of them here. So I just sketched them. This was before. The thing that just kills me is I've submitted over 500 planetary images to the Association of Lunar and Planetary Observers, ALPO. And this would be so incredibly easy with today's technology, with the fast ZWO, QHY, Player One planetary cameras. This would be so easy. And amateurs could have monitored this 24/7, all parts of the world. And it's just timing. The technology didn't exist back then where amateurs could actually take pictures of this. So can you see it full screen now? Again?
Yes.
Okay, great. So this ends the introductory stuff, with the comet. I know everybody basically knew all this, but so any questions so far regarding any part of comets?
Good.
Okay, you're good. All right, it's pretty basic stuff. So missions to comets. There were actually 5 are shown here, and there's one more, the Rosetta. There were actually 6 spacecraft that visited comets. Okay, successfully visited comets. And I'm going to go through the basics of all of them, focusing on the carbon organic content. So the first one was the Giotto mission to Comet Halley. Isn't that a beautiful, and this is what it saw. Isn't that gorgeous? We actually, for the first time in human history, ever saw a comet nucleus. So it's so great that, Fred Whipple, who proposed the dirty snowball, actually lived long enough. He was 80 years old to actually see his theory proven, Before he had indirect evidence, now there's direct evidence. He actually imaged it. So this is fantastic. So ESA's, the European Space Agency, Giotto, March 1386, went within 373 miles of the comet's nucleus, and it determined it to be a dark carbon-rich body, 9 miles by 7 miles by 6 miles. We don't think in kilometers in the United States. I mean, if I said 15 kilometers, people don't really know what that is. If you say 9 miles, oh yeah, 9 miles, yeah. So it's 9 by 4 by 6, and then the mass, and then the density, and then look, the albedo 3%, rotation period 7.4 days, and then look at that. You can actually see structure within here, which is outlined in this diagram here. So the nucleus showed hills and valleys, and the shapes be continuously altered by jets. 10% of the surface was determined to be active. At least 3 outgassing jets were seen on the sunlit side. And then the quality of material ejected was 3 tons per second. Can you imagine that? A ton is 2,000 pounds. So that's 6,000 pounds per second is coming out of this Comet. Oh my God, that just blows my mind. That's just incredible. And out of all this volume, 80% of it is water, 10% is carbon monoxide, and 2.5% is a mixture of methane, ammonia, and cyanide. It's a lot of cyanide in comets and other hydrocarbons. Also, the elements iron and sodium were also detected in trace amounts. And then here's a nice cleaned up image of it. This was March 14. So the ratio of the comet's light elements, excluding nitrogen, hydrogen, carbon, oxygen, are the same as the sun. So this implies that it's a very primitive object that's changed very little since the formation of the solar system. And Halley's Comet has twice the amount of heavy water, D2O, compared to normal water, H2O, as the Earth does. I have a slide when we get to the Rosetta mission. So just hold that thought, how heavy water, D2O, okay, deuterium is the heavy isotope of hydrogen. So an isotope is an element that has same number of protons but different number of neutrons. So hydrogen has 1 proton, 1 electron, and 0 neutrons. Deuterium has 1 neutron. And tritium, which is what's used for the hydrogen bomb, has two neutrons. Okay, so this is very stable. It's not radioactive, very safe. Okay, and also the Giotto spacecraft also flew by another comet here, Greg Skiloof, in 1992, but it didn't take any pictures and the instruments were damaged. I did an internet search. I couldn't find any information from the Giotto spacecraft on this, like any measurements or anything. So it was pretty much dead. But the important thing was it survived Comet Halley, and we actually got to see the nucleus, and Fred Whipple was vindicated. I mean, this is good stuff. And then spectroscopic organic molecules have been detected in the nucleus. Organic carbon occurs in 2 basic forms, inorganic and organic. Inorganic is carbon bonded to other carbon, and that occurs in 3 forms. Graphite, which is flat and slippery, diamond, which is tetrahedral shape and hard. And now, only since about the mid-80s, we've discovered that there's a 3rd form, fullerene, buckyballs. And so, but organic carbon is carbon bonded to carbon, hydrogen, oxygen, and nitrogen. And then you can add sulfur and phosphorus too. But CHON, CHON. So think of CHON, CHON. That's organic carbon. And then this is the atomic, the molecular weight of the ions formed. And this is carbon and hydrogen. And I have a whole slide on these. So I'll give you a basic idea of what an alcohol, an ether, ketone, and aldehyde is, etc. Okay. So we'll get to that slide later. So the important thing is here they found formaldehyde, which is embalming fluid, but it was actually in the form of a polymer, polyoxymethylene. And then if you heat that, it'll just degrade the formaldehyde. So, and then this is Halley's Comet in 1910. And this was actually the first comet that's actually photographed. And what's cool here is you can see a disconnection event. See it? Isn't that cool? You can see. And then obviously the time it was really, really close was May 4th and 6th, and then started the tail. And then what was cool is in 1910, as was mentioned earlier, entrepreneurs were selling gas masks to people who feared the passage that we'd be poisoned from cyanide from the tail of Halley's Comet. So any questions regarding the Giotto mission before we move on?
We're good here.
Okay.
I got a question.
Oh, sure.
All right, you name my favorite molecule, Buckminster fullerene.
Oh, yes.
Is that detectable spectroscopically?
Yeah, it would be, but I haven't read where they actually detected buckyballs in comets yet. They have found them in meteorites. Okay. I have here, I'm going to talk about this later. I also collect meteorites. This is the famous Murchison meteorite that fell September 20th, 1969 in Murchison, Australia. This is the one that has the amino acids, the fatty acids, the nucleotides. This has everything to jumpstart life on Earth. And this also has buckyballs in it too, and also interstellar grains, just a whole bunch of cool stuff. But they haven't detected it, to my knowledge, in comets yet. Okay. All right. So the next mission is the Deep Space One, and this was actually sent to image asteroid 69969 Braille, and this was launched in 1998, and it included an extended mission to go to Comet 19P Borley, and there were problems with it tracking, and the ultraviolet spectrometer failed, but it did measure the asteroid 1.37 miles by 0.37 miles, and a spectral type, it's a rare kind of Q-type asteroid dominated by olivine and pyroxene, and it's very bright. Notice how white it is. See, 34% as opposed to 3% and 4% for Halley. And then this is the picture that came out, and then this is a more processed, higher resolution of this. But this is the best. This is the highest resolution image of asteroid Braille. So in a way, some of these, many of these flybys had visited asteroids before they hit their parent comets. So I see that as a win, because you're getting something you really didn't intend to get. It happened to be in the path of the comet as you were flying by. So let's image it and learn more, so we get more bang from our buck. And then here's Comet 19P Borley, and this looks like a bowling pin, doesn't it? A nice bowling pin. Notice how different it looks from a Halley, and the entire nucleus is extremely dark, 3%, and but they all basically have the same albedo, density, and mass, and it has a lot more textures and a lot more features than Halley did, and it exhibits no trace of water ice or any water-bearing minerals. And a lot of the comet surface is inactive, okay, very little. And the nucleus is quite hot, ranging from 300 to 304 Kelvin. So I converted that to Fahrenheit, and that's 80 to 160 Fahrenheit. That's hot. And I did an internet search, and this always comes up, but they say the mechanism is unknown. So no one has an explanation as to why it would be that hot. And then gas here is appear to be escaping localized jets less than 10% of the surface. And ground base show that Borley to be a weak producer of gas and dust, releasing less than a ton of water per second. Notice Halley's released 3 tons of material, 80% of that being water. So you got 3 tons of material being released as opposed to 1. So it's not as active. And here's a lot of the terrains that have been identified here. And then the comet's nucleus exhibits an unexplained absorption peak at 2.39 microns right here. And then this is and then this is believed to be that of the polyoxymethylene, the polymer of formaldehyde, which was previously detected in Halley's comet. And then that's basically it for Deep Space One mission to Comet Borley. Any questions?
Not here.
Okay, good. All right, so deep impact mission to 9P Comet Tempel 1. Now, this was a cool mission. This was launched in 2005. And the whole idea of this, like it said, deep impact, was to shoot a projectile into the comet and then see what came out and measure the determine the material that's actually inside the nucleus of the comet, which is really cool. So this measures 4.7 to 3 miles, so it's pretty large. And then density, and it has a little higher dense albedo, 4%. Again, they're all very, very dark. This is very image enhanced. This would be as black as this if they didn't image enhance this. So a lot of times it looks grayer, and you would think, oh yeah, this is the true, image of it, but it's not. This is really boosted up the intensity, or else it would look like that and you'd see nothing. So here it is. So the projectile hit the nucleus on July 4th, 2005. So NASA planned this. This is kind of cool because 4th of July fireworks, and we had celestial fireworks in space at the same time. How cool is that? So the probe spectrometer detected fine dust and gas particles detected. They detected silicates, carbonates, smectite, which is a type of clay, metal sulfides such as fulgo, pyrite, amorphous carbon, and polyaromatic hydrocarbons. These are tar-like compounds. I'll talk more about these later. Parent volatiles included water, hydrogen cyanide, methyl alcohol, ethane, and then molecules such as ethane were produced post-impact. So these are pre-impact and these are post-impact. So, and then water ice was detected in the ejector, and the water ice came 1 meter below the crust. So that's really cool. So here you can see images from the spacecraft. Here pre, and then it hit, and then look at that. That's amazing. And then impact findings. This is in the infrared. Oh yeah, sure.
How did these spacecraft transmit post-impact data after it impacted the comet?
It was an
Oh,
impactor.
I guess through the they all have an antenna that's directed toward Earth, and they just, we're in constant
After the
communication.
impact, there was no spacecraft.
No, the spacecraft shot a projectile at the comet.
I think
Yeah.
it's an orbit. Yes, the projectile was
Okay.
destroyed.
It's like shooting from the, from the.
Okay.
Yeah, it shot a projectile. That's what you're seeing here, the effects of the projectile. And the spacecraft was moving this way through the comet, and that's how it detected it, and it just relayed the information to us. Yeah. Okay, so next, deep impact findings. So this is in the infrared, and then this is the intensity here. So this graph really isn't telling you much. This is just very water ice shows signatures at these wavelengths. Complex organic molecules. Look at that. There's little data there as far as anything specific, chemical structure, anything specific. And carbon dioxide is here. So that's all the information we basically got out of this. And then here, these are mineral species that were identified in the ejector cone. Okay, so amorphous olivine. Olivine is a magnesium iron silicate. Okay, and that's gem grade peridot. So if you look at a palisite meteorite, see all these beautiful green crystals? That is olivine. Isn't that gorgeous? Yeah. So that's olivine. These olivine crystals, okay? And this is nickel iron metal, but we're focusing on just the olivine crystals there. And then notice mostly magnesium iron silicates. This is an iron silicate. It's magnesium silicate. Olivine is a magnesium iron silicate. And then pyroxene too, same thing here. And then smectite, this is a clay. And then magnesium carbonate, and then polyaromatic hydrocarbons, which we'll talk about later. And so these are basically the the minerals that were identified post-impact. This was published in Science. So what's interesting is there was a crater obviously formed when this impactor hit. And so NASA wanted to actually see if they could image the crater, but this was a flyby. So the spacecraft flew right by and couldn't like be rerouted and returned. But the Stardust mission, which we're going to talk about in a little bit, went to Comet. This is pronounced Vilt 2. I don't know why it's spelled wild too, but it's pronounced Vilt 2. And this was actually, once it visited Vilt 2, it was redirected to go back to Temple 1 and revisited it. Isn't that cool? And it was called the next mission, New Exploration of Temple 2, of Temple 1. So it actually went back, and then on February 15, 2011, it actually saw the comet. And this was the first time that a comet was visited by spacecraft twice. And then why with that? Here it is. So here it is. It was identified. That's the little crater that it's estimated to be 490 feet in diameter and a bright mound around it, created by the material that fell back into the crater. And then this was the calculated energy that would have been released. Isn't that amazing? I mean, you divert a spacecraft that's already in another comet back to this one, and you could actually see the crater that was formed from the projectile. That's amazing. And then here's the Hubble Space Telescope image, and you can see how 3 minutes after impact, 12 minutes, 1 hour, 40 minutes, you can see the expanding plume here of dust and gas. Isn't that cool? And so any questions regarding deep impact and the next mission?
Not here.
All right. So the epoxy mission to 103P Comet Hartley 2. So this was this returned images in 2010, and this came within 430 miles of the comet, and it's peanut shaped here, and had several bright jets. Look at that. You can see a lot of bright jets, especially at this end and over here. And it's approximately 1.24 by 0.25 miles. So it's kind of a smaller comet nucleus, and same albedo, 4%. And what's interesting about this comet is it has carbon dioxide driven jets of water seen at the ends, most occurring at the small end. So these are carbon dioxide driven jets of water. And one unique thing about this comet was that it had an increase of cyanide gas. This has the most cyanide gas ever recorded. The cyanide gas formed the cloud more than 124,000 miles in radius compared to the comet's size of 1.24 miles. So isn't that amazing? I mean, the cyanide gas cloud was humongous in this comet. And then here we have, this is visible, and then these are infrared images. So you can see carbon dioxide is ejected from the active end, dragging dust and ice grains from the nucleus. So here's the small part. So carbon dioxide and ice are driven here. And then the grains fall back into the gravitational low of the waste. So a lot of them fall back and are redeposited here. And then water ice is retained in most grains, resulting in enhanced water vapor emission. And then here you can see it's glowing like crazy in the infrared with dust. So there's a lot of dust there. And the carbon dioxide, look, you can see in the visible, is limited to this area mostly. And then the water ice is where the jets are here and here. See? So that's pretty cool. So the infrared is showing a lot of what the visible is showing. And then, key findings. So it's a hyperactive little comet spewing out more water than most other comets its size. And the value of the deuterium to hydrogen ratio of water observed is very similar to the value observed in Earth's oceans. Hold on to that thought. I'm going to get to that very important graph when we get to the Rosetta mission, okay? So this deuterium to hydrogen ratio of this comet matches the deuterium hydrogen ratio of water in our oceans. Isn't that cool? All right. And then grain size mineralogy was dominated by carbon, pyroxene, and magnesium-rich olivine. And I showed you what olivine looked like. And inactive waste has probably been redeposited. A lot of these wastes here, there's a lot of redepositing of dust here. That's why it's so smooth and not as, rough as these edges. Okay. And then this larger end here has a lot of more features, blocky objects that are pretty high and everything right here. It's not as active in this area here. Okay. And then here's a rotation of Hartley 2. So any questions on Hartley 2?
Nope, good here.
Okay, good. And then the Stardust mission. The Stardust mission this is the one that went to Comet Ville 2. And before it encountered Ville 2, it stopped at, not stopped, but flew by an asteroid 5535 Anne Frank. And then this was the original image that came through. And then this is the post-processed image here. So this is the information on the asteroid. And notice how bright it is, 18 to 24%. See, it looks very white. It doesn't look dark. All right, so this is a much brighter asteroid. And this was the Stardust mission. This was the one I mentioned that went back to Comet Tempel 1 and looked at the impact, okay, from the Deep Impact mission. And this one was cool because Stardust was actually collected from this. And so the Stardust mission, it flew by Ville 2. Here's how Ville 2 looks like, okay? And during it collected dust and volatiles. And this actually collected interstellar grains, okay, and brought them back to Earth. Okay, how cool is that? And here they are. And they used this substance called aerogel. And being part of the Solar System Ambassador Program, they sent us an actual piece of aerogel. Here it is. They call it like liquid smoke. It's very, very fragile. And if I squeezed on it more, I'd shatter it. But it's like really, really cool. This was the actual stuff that they trapped, that NASA trapped cometary dust with. And there was actually a Stardust at Home, if anybody remembers that, a citizen science project that they had a virtual microscope and you could zoom in and see if you saw any of these something like this. And they had a little tutorial on how, and I looked through, I remember over 1,000 of these, and 2 of them were candidates. They emailed me back and they said, and then at the end they determined they weren't. So, but it was still fun doing it. But this is what happened when the impact hit. It formed this beautiful thing. And then this is actually how one of them looked like. Okay, so this is, and it's so this is abundant minerals including olivine, forsterite, and enstatite. Okay, and it had what are called refractory high temperature minerals containing calcium, aluminum, titanium. These are called CAIs in meteorite. And the Allende carbonaceous chondrite meteorite is full of calcium aluminum inclusions. This fell February 8th, 1969 in Chihuahua, Mexico. See that right there? That is a calcium aluminum inclusion. Isn't that gorgeous? Look at that. That's a big one there. I love this piece. complete slice. So that's what a calcium aluminum inclusion is, okay? And these are high temperature minerals, and they contain calcium, aluminum, titanium, okay? So they found a lot of that within these grains. That's what I'm saying here. That included olivine, forsterite, enstatite, and calcium aluminum inclusions. So this is the first time we actually brought back a sample from the tail of a comet. Isn't that dust tail of a comet? Isn't that fantastic? Okay, good. Now I could talk a little bit about organic molecules. Okay, so comet Vil-2 is rich in organic matter. So polyaromatic hydrocarbons called PAHs are composed of carbon and hydrogen and occur in six-member rings, benzene rings, which are also known as aromatic fused rings. So when you see these pretty pictures, and I'm going to tell you the secret of how to read this, okay? So when you see this, everywhere there's a little connection here is a carbon. So there's carbon, carbon, carbon. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons here. See 10. And now the hydrogens are not shown because it would be too messy. And so carbon has 4 bonds, as you know. So you got 1, 2, 3. So it'd be a 4. So there'd be a hydrogen here. So here you have 1, 2, 3, 4. So it'd be a hydrogen there, a hydrogen there. So there's 1, 2, 3, 4, 5, 6, 7, 8, Ca. Now there wouldn't be a hydrogen here because you'd have 5 bonds. 1, 2, 3, 1, 2, 3, 4, 5 if you put another bond there, hydrogen, see? So there isn't any here. So that's how you read these. All of these little things here are just a hydrogen, and then coming out of these is a hydrogen. No, each one of these is a carbon, and then coming out of here is a hydrogen. Okay, so that's how you read these. It's very, very simple, and these are very, very flat molecules. Okay, and so that's their geometry. They're very flat, and these are not true double bonds. This is what's called a resonance here. So sometimes you'll see a circle drawn instead of the double bonds. I personally like the circle better, but at least this shows the 4 bonds around the carbon. But these alternate, and so they're in a resonance here. So a lot of times you'll see not the double bonds, but a circle drawn. That's equivalent. Okay, that's the same. So that's what these polyaromatic hydrocarbons are, okay? And then naphthalene is, does anyone know what naphthalene is used for? A common household product?
Mothballs.
Yes, mothballs. But be careful. Dichlorobenzene is actually used for mothballs too. So look at the label and see if it says naphthalene or dichlorobenzene. But exactly, mothballs. Can you believe that? So we have mothballs in space. And and polyaromatic hydrocarbons are basically tar. So when you drove into the auditorium this evening, you drove on a carpet of polyaromatic hydrocarbons, and you'll drive home on a carpet of polyaromatic hydrocarbons. So asphalt and tar that's what it's made out of. This stuff here, it's actually the higher ones like these. So isn't that cool? So and then these were the ones that were identified in the stardust samples, and then also nitrogen-containing molecules, methylamine and ethylamine. CH3 is methyl. That's a methyl group, and then ethyl is CH3, CH2, and then the amino acid glycine was detected. Amino acids, the building blocks of proteins. Oh my God, that is so cool. That's the first time an amino acid has actually been detected. And these are necessary for life. So astrobiology is really big. That's one of my personal interests. And it's really cool because like I said, I double majored in pharmacy and chemistry. And, I never imagined that there'd be organic compounds in space and in meteorites. Oh my God, once I learned they were in meteorites, I started collecting meteorites, and then they're in molecular clouds. There's all these, organic molecules, and it's like, oh my God, I can actually use my organic chemistry knowledge for astronomy. So that's really cool. Okay, so this is good. So remember I said in Hallie's thing they mentioned alcohols and ethers and all that stuff. Okay, so this is a little crash course in organic chemistry. So if anyone's had organic chemistry formally, I hope you don't have nightmares today because tonight it's a very difficult course. So alkanes, just CH3CH2. These are tetrahedrally bonded. Alkene, if you have a C double bond, C, it's called an alkene. If it's single bond, it's called an alkane. And if it's a triple bond, there's a carbon here, okay, and a hydrogen there. It's called an alkyne, okay? So single bonds, alkane, double bond, alkene, triple bond alkyne, and then the benzene ring we mentioned before. It's also called a phenyl group, okay? Has its own vocabulary. Now an amine, now whenever you see this lone pair of electrons, it's called, that means it's very reactive. This is where reactions take place. A lot of these compounds, see, you don't see lone pairs of electrons. They're not very reactive. So a lot of these, the lighter ones are actually gases, or if they're heavier, they tend to be solvents. Benzene is a solvent, okay? Highly carcinogenic, but a solvent. And so it's, and a lot of these are carcinogenic. And so you have amine here, and then an alcohol. So an alcohol, you have CH3OH. That would be methyl alcohol, okay? Which will cause blindness if ingested. And then CH3CH2, which is an ethyl group, is called, that's why I call it ethyl alcohol, CH3CH2OH. That's the drinking alcohol, okay? So that's the alcohol in the beer, wine, all liquor, okay? CH3CH2O. And ether, dimethyl ether, that was used in anesthesia before. That would be CH3CH3. And then alkyl halides. This is when you have these, what they call halides, fluorine, chlorine, bromine, iodine. They have a lot of electrons, so these are very reactive. And they're used a lot as what they call leaving groups, so to make the reactions go easy. And then a thiol. Remember, Carl Sagan said there were thiols found in Titan and all that. This is what a thiol is. CH3 here, SH, okay? And then an aldehyde, so if you have CH3C double bond H, that's that would be an aldehyde. So double C double bond OH. And then if you have CH3CH3 with a double bond O here, that would be acetone, CH3 double bond O, CH3. That's nail polish remover. And then an ester, CH3, and then a CH3 here. So you have this double bond OO. And esters tend to smell really nice. They a lot of natural products that smell really nice, like cinnamon and stuff, would have ester groups to them. And then carboxylic acid is C double bond OH. And if you have CH3C double bond OH, that's acetic acid, which is in vinegar. So if you had a salad today, you had a carboxylic acid, you ingested a carboxylic acid, acetic acid. All right. You have an amide, CH3C double N, and then you add other groups here. So that's what functional groups are, okay? They contain what they call a carbonyl, a C double bond O, and these are very reactive, okay? They found the element sulfur in Vil2, and the deuterium hydrogen content is up to 3 times that of Earth's oceans. Keep that in mind, okay? And the isotopic ratios suggest that the organics were a result of pre-solar nebula processes. So this was formed during the beginning of the solar system. So this is really great stuff. Okay, and then here's questions regarding Vil2. I love this. Right foot and left foot. It does look like a foot, like you stepped in mud, doesn't it? I like that, right foot and left foot. So, any questions regarding Vil2, the Stardust mission?
think we are good?
I don't think we have any questions here. We are running a low on time, so.
Okay, I'll go really quick. And then Rosetta mission, this is the last one. Okay, so Rosetta was the last mission, and this went to asteroid. No one can pronounce it, it's very difficult. Everyone calls it 67P. And then this is a Jupiter family comet, orbits every 6.5 years, and it actually orbited the comet. All the other ones were flybys. Okay, this actually orbited the comet and sent information back to us, and it actually had a lander Philly that landed on the comet, and so and we had more bang for our buck. It visited asteroid Steins here. And here's the information on asteroid Steins. And this is, and notice it's bright. Albedo is, did I put the albedo here? Yeah, 34%. And it's believed to be an E-type asteroid, which is the parent body of an Albright chondrite. And here's an Albright chondrite. It's called Pina Blanca Springs. It fell in Texas. And notice how white it is, see? Very bright, 34% albedo, and notice how dark Murchison is, which is closer to the cometary nucleus, see? So differences in albedo, very important. Okay, so that's Steins. You can read a lot of this for yourself. And then Lutetia, this is a huge asteroid. Look at this, 82 by 63 by 47 miles. That's huge. And it's classified as an M asteroid, metallic, but it's not metallic. It actually has the surface of a carbonaceous chondrite, which is this, like Murchison. But the reason it's M is because it may have metallically enriched silicates, and so the spectra focuses in on that, and that's why it's classified as an M-type asteroid. But really, it's a carbonaceous chondrite type of asteroid. And then here's the nucleus of CG here. Look at all those jets coming off. And you can read a lot of this for itself. It has so little gravity. Look at this. Time to fall 1 meter, which is slightly over 3 feet, takes 90 to 120 seconds. And then this is kind of cool too. It's double lobed, and the way it rotates, it has seasons. So it stays, it tends to stay. The northern hemisphere experiences a long winter, and then the southern hemisphere remains long, dark, and cold. So it's kind of interesting that it has seasons, whereas the other comets do not, nuclei do not. This just tells you basic facts that I already mentioned. Here, it's double lobed with a head, body, and tail, and it's believed that these were small cometesimals that gently bumped each other and stuck together. It's got a lot of detail here that's been well studied. The neck has active jets, and a lot of the mass falls back, causing mantling. And then this, you can read here, just high porosity, 2 lobes. And then this shows the a lot of the features here, a lot of details on the features. Back to organic molecules, my favorite. So electrons and not ultraviolet photons are responsible for breaking up water and carbon dioxide. So they found molecular oxygen and nitrogen, and then CH3OH, this is methanol, so that was detected. So the compound hydrogen bromide has been detected for the first time. And then Rosetta detected noble gases. This hasn't been detected in other comets, krypton, xenon, and argon, okay? And then the various isotopes. And the high abundance consistent with the forming in the colder outer reaches of the solar system. And then here, this is the slide that I've been alluding to. Remember, I always mention the deuterium hydrogen ratio, right? So deuterium has a neutron and and then hydrogen does not. Okay, so you look at this ratio. This is Earth's oceans, the ratio of deuterium and hydrogen. And it was originally believed that during the late bombardment period, Earth's oceans came from comets. Because look, Halley's Comet is giving us three tons per second of material, and on the lower end 1 ton per second. Okay, so if they crashed on the Earth, that's a lot of water, so that would account for Earth's oceans. But no, if you look at the deuterium and hydrogen ratio, they're all high. These are all the comets. 11 comets have been measured, and only Hartley 2 right there matches. All of them do not. Notice they're all higher. So the idea is that comets, this questions the common belief that, the Earth's oceans came from comets. They didn't. So, but then a lot of meteorites, like the Murchison here, has 20% water. So if you were to heat this, a lot of water would come off and evaporate off. So if you have many more chondrites coming in, these meteorites, that could account for Earth's oceans. Isn't that cool? And this is an interesting fact I found. Earth's oceans have 1 atom of hydrogen, 1 atom of deuterium, heavy hydrogen, per 6,420 of hydrogen. So next time you're at the beach swimming, think about that. You're swimming in an ocean of deuterated water with a lot of deuterium in it. I think that's kind of neat. And so the Philly lander crash lands on the comet. What happened is the Philly lander was going to land and take data, but none of the harpoons fired to anchor it down. So it actually tumbled into this little dark area that never got sun. And so the batteries have 57 hours, and it performed as many scientific experiments as it could. And then here it collected, and then it detected 16 organic compounds, and 4 in yellow have never been known to exist in comets. Methyl isocyanate, acetone, propionyl aldehyde, and then ethylene glycol, which is antifreeze. That's kind of neat. So the Philly orbiter detected all these organic compounds. And look, almost 81% water. And then they also detected the amino acid glycine. Okay, so now we have 2 comets that have glycine, the amino acid, the 67P and also VIL2. And phosphorus has also been detected. And phosphorus is key in living organisms. It's the backbone of DNA and RNA, and also ATP, which gives energy to cells. So this is really cool stuff. And then the Rosetta mission finale, you can read this for yourself. It went down. It took 14 hours to drop down. And then as it dropped, this was a very close-up view of as it went down, and then loss of signal, and it was over though. So any questions on the Rosetta mission?
That's good.
And then proposed future missions. Now, all these missions started in the mid-1980s and went to about the mid-2000s. So there's 3 that are on the drawing board. The NEAT, Nucleus Evolution and Activity Tour. This is planned to go to this comet, Watchman. And this one is known to have fragmented in 1995. So this will be the first spacecraft to visit a fragmented nucleus of a comet. So that's kind of neat. So there's no proposed date set. And this one, Comet Astrobiology Exploration Sample Return, this is going to go back to 67P, but it's not going to, the Rosetta mission orbited it and collected, material from the dust tail. But here it's actually going to land on the comet and collect a sample of the surface and bring it back to Earth for laboratory analysis, just like the Rosetta mission, just like OSIRIS-REx and the Hayabusa 2 missions to asteroids Bennu and Ryugu. So this is going to be cool. And the proposed date was last year and this year, and it hasn't been launched. So this is on the back burner. And the Comet Interceptor, this is interesting. This is going to be parked in space at a Lagrange point, and it's going to wait for a long period comet like Hyakutake to come in, and then it'll kick in and follow the comet, and then it'll release 2 probes and observe it from multiple directions. And so that should be cool. So this is planned by European Space Agency for 2029. So hopefully these will actually come to fruition at some point in the future. And that's it. And these are my pictures. I'm not going to win any astrophotography awards, but this is my first of Comet Halley on March 12, 1986. This is in Jamestown, Rhode Island, Beavertail State Park, if you've ever been there. That's basically how it looked with naked eyes. It's just a 20-second exposure or so on 1600 ASA film. And I remember thinking 1600 ASA film just came out, and I thought, man, how can anything get better than this? Man, was I wrong. The digital age just and then here's Comet Holmes. This is the one that was just pure coma. Remember I mentioned? So you can see it here, just the coma. And then Comet Macaulay. I lectured to the Saguaro Astronomical Society in Arizona, and Don Macaulay was actually in the audience, and so I actually lectured to him, and I informed him that I saw your comment. I gave him this very lecture, so that was kind of cool. And now I'm lecturing to Steve O'Mara. Wow! So, and then here's Comet Hyakutake. This is a photo I took in 1996, the pre-digital ages. And I couldn't find mine of Hale-Bopp. And then just 2 more. Here's Comet Neowise. This was during the great COVID shutdown. This was combined in deep sky stackered from Nikon D300 12 megapixel camera. Here you can see the dust tail and the plasma. And then this is my single image of Comet Chichen-San Atlas. Can you see maybe the anti-tail closer here? See a little line there? I think you can see it a little better here. Yeah, you can see it right there. It actually extends all the way down. But so that's it. So any closing questions, comments?
Good?
You're good.
Great survey, yeah. That was great, thank you.
Okay, I hope you enjoyed it.
So there you go. So next meeting, we'll have Diane speaking to us. So June 12th. Right? Meeting is adjourned.